You're not the one. Okay. All right. So quizzes, I forgot them in my office, but Sun is on his way with them. So, but this is just the average. It's pretty good. Average compared to last year, it's pretty close. Last year it was 21, so you did a little bit better. So if you're at the average or higher, you're in very good shape. If you're lower than average, don't worry, it's not the end of the world. It's out of 30 points, equivalent to 1 lab report. So it's not a lot of, don't agonize over it. There is a midterm next Friday. Not this Friday, the following Friday. That's the one I want you to study well for. It's 100 points. So, and it's not a lot of information, new material after the quiz. So you already studied most of the information, just review really well, and a couple of lectures in addition. So what would be included in the midterm is everything up to spectroscopy. So I'm going to finish AA today. On Wednesday, I'm going to finish UV vis spectroscopy. And then there is NIR, which I won't get to finish before your midterm. I have to stop and start with proximate analysis because next week we start moisture. We'll get to NIR later. For your midterm, so everything up until Wednesday's lecture, okay, this coming Wednesday. So you have a week to study without new material. That's for the midterm. Okay. Any questions about the midterm? There is an example from last year posted on Canvas. As always, after you study, try to solve it. If you feel like you solved it correctly, then you are good to go. It won't be the same questions, but similar kind of concept. Okay, I need to go to the right screen here. Okay. So let's review a little bit of principle before today's lecture. So what are the different species of matter that can be analyzed using spectroscopy? Andrew? I changed your name. Okay, quizzes are here. Perfect. Can you have one? Okay. Thank you. Solid, liquid, and gas. Wait, is it just? Hold on, you're mixing things together. My part.
You mean like ions and atoms?
Atoms and molecules. Yes. Species of matter that can be analyzed. So what can we analyze? Can analyze atoms like in atomic absorption and molecules. Everything else we use spectroscopy for are mostly in form of molecules. So what are different forms of radiation matter interactions? Form of interaction we talked about last time. Abi? Absorption is one. What else? Sally?
Light scattering.
Light scattering. Paige? No, sorry, not Paige. You're sitting next to each other. Gretchen, sorry.
Diffraction.
What's that?
Diffraction.
Diffraction. Go ahead, Maya. Yes. Fluorescence. Yes. Thank you. All right. So absorption, fluorescence, light scattering, diffraction, and there's also refraction, and there's interference as well. Okay. So what are some applications? No, before that, what are the spectral region most relevant to food analysis? Go ahead, Grace.
UV, visible, and infrared.
UV, visible, and infrared. Absolutely. These are the ones that we care about and utilize in food analysis. Okay. Now, what are some applications? Valerie?
clarification on the structure.
Yes, so identification, elucidation of structure, quantification. So yes, quantification carries a lot of different categories. What's the difference between electronic and vibrational energy, and to what spectral region each corresponds to? Okay, Paige.
So electronic is like the magnitude of the energy difference. And then vibrational is how it vibrates in orientation, or like its constant functions. And usually vibrational is correlated with IR.
Yes.
And electronic is UV.
UV and vis. Okay, so electronic electronic energy is associated with the energy delivered by UV and visible light. And electronic has to do with the electrons shifting to higher shell, higher level due to picking up energy. So that's hence the electronic, the valence electron of the atom or molecule. Vibrational energy, it has to do with the vibration of the bonds within a molecule. So like you hear stretching and bending of bonds. This happens when the molecule absorbs light in the IR region. Okay, what's the difference between absorption and fluorescence? This one should be easy. In absorption, what are we measuring? In fluorescence, what are we measuring? Oh, come on, you know that. Hold on a second. So what's the difference? What is fluorescence? What does it mean when a molecule fluoresces? Okay.
It is emitting a small amount of light that is absorbed.
Yes, fluorescence is when the molecule, when it's going from excited state to ground state, it can emit a photon of light at a lower energy than the photon of light that hit it. So every molecule that can absorb light goes from ground to excited state, but it doesn't stay there. It goes down to ground state. It can go down by dissipation of heat, 100%, or it can go down by dissipation of heat plus emission of photons. So that's why the photons that are emitted are of a longer wavelength and smaller energy than the photon absorbed. What is the difference between diffraction and refraction of light? Go ahead.
Okay. The refraction is the change in direction of the waves, and then diffraction is the bending of the waves.
So refraction is change of direction, and this is used in refractive index. Diffraction of light is when the beam of light gets diffracted into multiple wavelengths. Then you use that in like when you want to generate a monochromatic light for measuring absorption for quantification. Because we'll talk about Beer's law on Wednesday. For Beer's law to be applied, you have to have singular wavelength for absorption to relate absorption to concentration. So diffraction of light is important because when you have a source of light, you want a singular wavelength to measure absorption at. So the light gets diffracted and a singular wavelength is selected for measuring absorption. How does the wavelength impact the frequency and energy? Okay, go for it, Sarah. Yes, so when you have shorter wavelengths, you have multiple occurrences within a unit time, so it carries more energy. You would have higher frequency, higher energy. With longer wavelengths, you have you have less energy and lower frequency or occurrences per unit time. less occurrences per unit time, then therefore less frequency, therefore less energy. All right, armed with this knowledge, we can go into atomic absorption. All right, so in atomic spectroscopy, actually, you have absorption and emission. So you can do atomic absorption spectroscopy, or you can do atomic emission spectroscopy. What you did in the lab is atomic absorption spectroscopy. Most of you, there's two more groups on one side. Okay, so under atomic absorption spectroscopy, most common is flame atomic absorption spectroscopy, and that's what we're doing in the lab. And then there is electrothermal atomic absorption spectroscopy, less common, it exists, but we'll talk about it briefly. The atomic emission spectroscopy, we have flame emission spectroscopy or flame photometry. We'll talk about it briefly, but the most common one used in labs where you have to analyze a lot of elements, whether in food or in soil, they use this ICP AES. ICP stands for inductively coupled plasma atomic emission spectroscopy. This acronym will show up later. Okay, so what do we do with atomic spectroscopy? It's directed towards elements, mineral elements. So looking at calcium, iron, magnesium. So elements that zinc, copper. So a lot of elements that are minerals for us, essential minerals for us. So we measure those in food, but also there are toxic and heavy metals that we don't want in our food that we measure as well, like lead and mercury, for example. So here's your favorite periodic table. Everything in thing can be analyzed by atomic absorption. And like I said, we look at essential nutrients in food, and they are presented in table 9.1. There's also toxic elements such as lead, mercury, cadmium, nickel. And USDA has a nutrient database that includes a lot of these elements in different food products. Not complete list, but a lot of them. So in atomic absorption or emission spectroscopy, what happens is it is electronic energy absorption. So there are atoms, not in molecules, so you don't have vibration, you don't have rotation. You have electronic energy absorption. So the photon of light hits your valence electron, the valence electron goes to a higher shell, it's an excited state, and then upon release, upon going to ground state, there is a release of heat as well as a photon of light at lower energy, longer wavelength. So basically, every element has its own spectra. In a sense, it absorbs light in a specific region. And of course, they have lambda max, which is the wavelength at which you have maximum absorption. And also, every element emits light, again, at longer wavelength, lower energy. And again, there is for every element, there is a lambda max for emission. So in atomic absorption, what happens is again the same thing, ground state to excited state. This should be frequency, the sign for frequency. I don't know why it's not showing here. And here we don't have rotational, vibrational. We only have electronic stages of energy. So basically, we don't have these. So this is how it looks like for every element. The increment increase in energy looks like that for atoms. Okay, so what some of you or most of you already done in the lab is you prepared your sample and your elements are solubilized in solution of acid. And now you have your minerals in the form of molecules. So you want to convert them to atoms in the gaseous state. not ions. You want them to be atoms in the gaseous state to measure absorption of light. So you have your sample, the sample gets aspirated, nebulized into fine mist. So you'll have small particles of liquid going into the flame or plasma. Flame for atomic absorption, plasma for atomic emission. So goes into the flame. What happens there? The molecules vaporize, the liquid vaporizes, and then the bonds are broken. So there's enough energy in the flame to break the bonds, and then you would have atoms in the gaseous state. So now we don't want it to go into the ion state. So we regulate the flame temperature, especially in flame atomic absorption or emission. The flame can be too hot. If the flame is too hot, then we get ionization, and atoms and ions absorb or get excited at different wavelengths. So we want to make sure that the flame is hot enough to break the bonds, but not to convert atoms into ions. So the step of controlling the flame is essential in atomic absorption. So the next important component of atomic absorption spectroscopy is the source of light, which in this case, the most common one is hollow cathode lamp. It's hollow because it contains an inert gas, argon, and you have a cathode and you have an anode which voltage source comes to. So here, the cathode is made up of the metallic form of the element of interest. If you're measuring calcium, it's made up of the metallic form of calcium. If you're measuring iron, it's made up of the metallic form of iron. So when the voltage source is applied, then the cathode emits light in the region of that element, in the allowable energy regions for that element. So usually every lamp has one cathode. Some lamps can have two cathodes, like the calcium magnesium lamp can have two cathodes. But in general, every lamp has one cathode. So when we're measuring calcium, we put the calcium lamp. When we're measuring iron, we have to have the iron lamp. So we change lamps based on what elements we're trying to measure. So in lab, you either change lamps or will be changing lamps for calcium and iron determination. The other less common lamp source of energy is electrode-less discharge lamp. So here again, you have a hollow tube, you have an inert gas, and the discharge in this case is produced by radio frequency instead of electrical current. So instead of a voltage, you have radio frequency. It's commonly used with volatile elements, but we don't have this kind of lamp in the atomic absorption we use in the lab. These are old atomic absorption. I should put the newest picture. We started 15 years ago with this very old atomic absorption. We got upgraded, and now we have an even newer unit that you used or will be using in the lab. But the compartments are very similar. So the compartments are the same. So you have the lamp source where you insert your lamp. You have the aspirator and the nebulizer. So here you put your sample, and then the little capillary tube that aspirates the sample into the flame. And then the nebulizer turns it into mist, and then the particulate in the flame get the energy. So the energy breaks, first of all, evaporates the solution and breaks down the bonds. So now you have the atoms in the gaseous state. So you have your atoms here. Then the light source is emitting light in the allowable energy from that element. The element absorbs light. The remaining light gets to the detector. And the difference in the light from initial to the one reaching the detector will be converted to electrical signal, and then you can get measured absorption that way. The software gives you the calculation, and here I'm emphasizing that this has to follow Beer's law. So basically, absorption is linked. So in this case, your sample holder is the flame. Instead of having a sample tube or a cuvette, your flame is your sample holder with distance. So absorption is related to absorptivity, the length of your cuvette or sample place to concentration. And we'll talk more about Beer's law on Wednesday. So Beer's law is only applied when we select for 1 lambda. And this is a little bit more of illustration. So you have your light, the flame, absorption happens, then the remainder of the light goes in to the detector unit. In the detector, you have a monochromator. So the monochromator is going to have a unit in there, diffracting unit that diffracts the light into another mirror. And then here you control the slit where a specific wavelength passes through and you get the absorption. So what happens here inside of this detector, when the light hits the detector, the one that we have in atomic absorption is called photomultiplier tube detector, PMT, photomultiplier tube detector. So in this detector is photomultiplier because when the light hits it, you get, so the light that comes after absorption hits the cathode, an electron gets kicked off into a dynode that multiplies the electrons. So there are multiple dynodes that multiply the electrons that are pushed off the surface, and then you have the signal amplified, so you have better sensitivity. So that's what it is multiplier means for, photomultiplier tube. They're multiplying the electrons to enhance sensitivity. So that's the type of detector you have in the atomic absorption, yes.
So when we actually ran this in, when we ran this in atomic absorption, when we got the slit, it came in a unit as H. It would come in like nanometers or millimeters. Is there a reason for that?
When you measure, why you're measuring absorption, you're not measuring wavelength. Is that
saying
your
the size of the slit. Yeah. It says 0.2 H or 0.7 H. It's just good with the H. Yeah.
Oh, I'm not sure.
Because like
Distance. I don't know.
okay, the cat like offered us an extra question. So
Okay, answer it and let me and Kat know.
okay, well you already know. So I'll just like
I don't know what
she
this
just
is.
said she just wanted to know if it was okay.
Huh?
She wanted to know if it was okay. 'Cause you
Yeah,
go ahead.
okay, I'm okay. Get it, get that information. I don't know.
Okay, I will discover.
Okay, so when the light hits, you have specific spectra that can, where the elements can absorb light at, and then the specific wavelengths that you select that goes in, you see the decrease in the light that reaches the detector. So the light gets absorbed, and then the whatever reaches the detector is less because the elements absorb that particular light at that particular wavelength. Any questions here for moving on? Okay. So this is a less common atomic absorption unit. You don't have a flame, you have a graphite tube. So in here, you have a platform that gets heated up. Instead of having a flame, you put your sample on this platform and the temperature goes really high, 2000 to 3000 C. And then your sample evaporates, your molecules now in the vapor, and the energy is enough to break the bonds. And then you have your atoms in the gaseous state, and the source of light is the same. Now, you have better threshold, that means better sensitivity. You can detect at much lower concentration. So if you don't have a sample, if you remember, if you did it in lab, you put 10 milliliter sample and then sample gets aspirated. So there's a lot of sample that needs to go through to get your absorption. But here you can put a drop of sample, 1 ml, even less, and then you can get measurements. So if you don't have very much high volume of a sample, then that would be a good choice. It's expensive, higher maintenance potentially, lower sample throughput because it's hot. You cannot just open it with another sample like you would do with the atomic absorption where you have the capillary tube, you just take out sample and put another sample in. It's much easier. So this is more difficult to operate, can potentially cause low precision and matrix interference. So it's not very commonly used. Let's leave it at that. Now, flame emission, it's used for specific elements actually. Those elements such as sodium and potassium, they absorb energy at a lower energy, basically a lot longer wavelength. So they get excited at low energy, so low excitation energy. In this case, in flame emission, you don't need the lamp. So you have your flame, and the flame is sufficient to break bond and excite the elements. So no need for lamp. You still need to do the atomization, and the source of excitation is flame, and then now we're going to talk about plasma would be also the source of excitation. But in this case, flame causes atomization and also excitation. But this is only for elements that have low excitation energy, such as sodium and potassium. So flame emission spectroscopy, you have a monochromator in the detector. Flame photometry, you don't have a monochromator, you have light filters, basically. It's much simpler unit, but does the job if you only want to measure sodium and potassium. But now, going to ICP, this is the most common flame or atomic emission type of spectroscopy currently used. And again, it is inductively coupled plasma atomic emission spectroscopy. Inductively coupled because you have radio frequency that basically gives energy that heats up and generates the plasma at really, really high temperature. And in this case, you have the argon gas, which radio frequency causes the argon gas to form ions and to get heated to really high temperature, generating the plasma. And this plasma is the source of atomization as well as excitation. In this case, you don't have lamps. The plasma atomizes and also excites the atoms, and when the atoms go from excited state to ground state, they emit light, and you measure emission of that light. So there's no lamp source in plasma units. So again, you put your sample, it gets aspirated, you have the nebulizer, you have the argon gas, and then you have the source for the energy, the radio frequency power, and the radio frequency gets transmitted into argon, generating the plasma. And then there you have your samples are in the plasma now, they're atomized and they get energized. Then when they're relaxing, they emit light. When light is emitted, then it goes into the detector unit. In ICP units, there are different types of arrangements of detector. Sometimes you have this very convenient type of detector where you have multiple photomultiplier tubes, several of them. Here you can see 1, 2, 3, 4, 5, 6, 7. So the grating system diffracts the light and you can simultaneously measure 7 elements in this case. A particular wavelength can reach different photomultiplier tubes, and you get fluorescence reading for 7 elements simultaneously. So this is pretty convenient. Sometimes you have only one photomultiplier tube, but you can sequentially change the lambda, and then you can get sequential reading of your different elements. So from one sample, you have multiple elements emitting light. So you can either measure 7 simultaneously or sequentially. Have one multiplier tube and you just change the slit opening to allow different wavelengths to happen sequentially. So in more advanced detectors, we have the issue detector. We'll talk about it later. Charge injection detector, we'll talk about it in a minute there. All right, these are just structure of a closer look to the plasma and the temperature at each location. FYI, nothing much here. So the sequential PMT, when we have one PMT, the simultaneous when we have multiple, and the initial spectrometer allows detection of more than 7 multiple elements at a time. It kind of works similar to PDA concept, photodiode array concept, but here the concept is a little bit different. But what happens here, instead of having multiple photo multiplier tube detectors, you have this one detector here where you have your light that goes in, the emitted light that gets diffracted. You have a grating system and a prism that diffract the lights into multiple wavelengths, and they can simultaneously be read. So here you don't need a photomultiplier tube, you don't need obviously a lamp, and you get detection for a large number of elements at the same time. This is a very expensive detector. You can see here $70,000 to $90,000 is the cost of this detector. So you won't see it in a teaching lab. You would see it in a lab that constantly measure a lot of elements, like the soil lab here at the University of Minnesota potentially has this detector. They have the ICP, inductively coupled plasma, and potentially this detector because they analyze a lot of elements in the sample. So preparation of your sample. So some of you did that already. We're measuring elements in different food samples. What we're doing for the lab mostly is dry ashing. So what we do is we take your sample, we weigh it in a crucible, and we subject it to really high temperature, 450 to 500 degrees Celsius in a muffle furnace. So your organic matter is burned off. So like your organic matter becomes CO2, SO2, NO2, H2O. So everything gets converted to or oxidized, and what is left is in your inorganic matter, which includes your minerals. So that is dry ashing. We'll introduce wet ashing when we cover the actual ash analysis lecture, but wet ashing meaning you digest your sample in really concentrated acid. So instead of putting it in the muffle furnace, you digest it at high temperatures still, but with a very concentrated acid, like nitric acid, for example. So sometimes it's a combination of nitric acid and sulfuric acid. So again, the concentrated acid is also going to kind of oxidize your carbonic organic matter. And these will also be evaporated as fumes, CO2 fume, NO2, SO2 fumes. And again, what you end up with is your minerals solubilized in your acid solution. Then you would dilute it, and then it would be ready for measuring in the atomic absorption. Sometimes we do direct injection without dry ash or wet ashing, but this is for samples such as mineral oil, for example, does not need to be pre-ashed. So here I highlight in the box few things: reagents, blank, standards, and lab glassware. So when we work with reagents, especially acid, if we are diluting our minerals in acid, we want to make sure that the acid we use is mineral free, so does not contain the minerals of interest. So, but at the same time, there might be some contaminants coming from my reagents. We use DDW, like the ionized double distilled water, but there might be some elements there still. So blank is very important. So in the lab, some of you already saw there was an empty crucible that you would put reagents in it and treat the blank the same way you treat the sample. So if you're solubilizing with concentrated HCl, your minerals, you put the same amount in your empty crucible. And then you carry it through the entire dilution step the way you do your sample. Yes.
Do you care about the reproducibility of regards to dry hashing and wet hashing? Does it have any difference?
No, it doesn't. You need to be very well. If you do wet ashing, you need to have training to do that because it's much more involved than dry ashing. Dry ashing, you weigh your sample, put it in crucible, and put it in the oven, and you don't do anything. In wet ashing, there's more involvement. You as an experimenter, you will be more involved. So you need training before you can do wet ashing. But sometimes wet ashing is better than dry ashing if we have elements that are volatile. For example, iron is a volatile element. If you had a sample in the lab, baby cereal or almonds or I don't know what other the Cheerios, your iron might have been underestimated. And that's because under dry ashing conditions, iron can volatilize. So you can lose some of your iron by volatilization during dry ashing. But in wet ashing, you are heating at much lower temperature and your iron remains soluble with the acid and does not get evaporated. So sometimes you have to do wet ashing if you are after minerals such as iron and zinc that are volatile minerals. So dry ashing you can end up having an underestimation because of that. So anyway, you prepare blank alongside to account for any contamination from crucible, from the reagents, from water. So you make sure that you account for that. So you run your blank alongside your samples and you deduct the value, the absorption of the blank from the absorption of your sample to correct for any contamination that comes from reagents. You prepare pure standards and you prepare them in the same acid solution that you prepare your sample so that you can construct a standard curve to determine your concentration of calcium or iron or whatever. Labware or glassware, they all have to be cleaned and acid washed. So all of the glassware that you've had in the atomic absorption lab or you will on Wednesday, these are all being acid washed. If there are any contamination of mineral in the beakers or in the crucible or in the volumetric flask, these all have been washed with acid so that the acid solubilizes any minerals left in your glassware so that you don't have contamination. The blank doesn't account for contamination coming from glassware because one beaker might have an element contamination and another beaker might not. So one volumetric flask might have a prior contamination, another volumetric flask may not. So the blank does not account for contamination coming from lab glassware. So they have to all be washed and acid washed so we know that they don't carry any contaminants. So Calibration, yes.
During dry ash, you really need to clean the crucible per se.
Yes, absolutely. Before you use the crucible for your sample, all the crucible acid wash and ash and before you.
But trying to understand like.
No, it's because we don't want any. You add
So-
and then-
Can I have it? Okay, so when you have lots of crucible in the lab, each might have been used for different samples. So before you use them for particular mineral analysis, you have to take these crucible, acid wash them all,
Oh, okay.
and then ash them all, then now they're all clean and have similar contamination as them.
Okay, I was gonna say, it's like, just do a general ash, a general value.
Yeah.
And not,
No, once you start with a very clean crucible, then you will be just analyzing the ash in the sample in that crucible after it's been cleaned. Does that make sense?
sure, but
Huh?
I'll let you continue with the rest. Just gotta think about what I say before I say.
Think about it, yeah. All right, so we need to, yeah, you raise your hand? Okay, so we need to select standards that are very, very pure. So often 99.99% pure. And we want to make sure that we select concentrations where we have linear correlation between absorption and concentration. Some minerals, this linear concentration or linear relationship happens at very, very low concentration, 1 ppm to 10 ppm, for example. Others have a linear range wider than that. Start with like 1 ppm to 20 or 30 or even 80 ppm. So we have to select the range where we have linear relationship and prepare the concentrations of our standards accordingly. Otherwise, Beer's law cannot be applied. You need to maintain linear relationship between absorption and concentration. Sometimes if the concentration is high, then we don't see a change in absorption that is linear. You cannot do prediction in this side of the scale. So, for example, in lab, if you are determining the concentration of calcium in cheddar cheese and you got a point of calcium way above your standard curve. So your standard curve linear range is here and you got a concentration here. You can't trust it. You can't tell if this is a correct prediction because it was outside of your linear range of your standard curve. So that's why when we give you these samples, we predetermine the dilution. We determine the correct dilution so that you prepare your sample, you dilute it, therefore the concentration will lie within your standard curve, not under the lower concentration and not over the higher concentration. There are interferences that we usually work with. So if we are determining the concentration of iron, we need to select a wavelength that's not necessarily lambda max for iron, because the lambda max of iron is very close to the lambda max of zinc. So if we want to make sure we're measuring iron, not iron and zinc, we try to select a different wavelength where zinc doesn't absorb, but iron does. Might not be the optimal or the lambda max for iron, but we want to make sure that we don't have a spectral interference. Background, this is a cause for overestimation. So you have a question in your lab report, what can cause overestimation? Overestimation can be caused by incomplete atomization. So if the flame is not hot enough to break the bonds, if the acetylene to air ratio is not the right ratio, acetylene is the fuel, air is the source of oxygen to ignite to produce the flame. If you don't have the right temperature, your molecule might not break. So the molecule is going to scatter light. So less light from the lamp will reach the detector. So the detector will think, now less light reached me, therefore there is more absorption. And will give you a higher absorption, and that will lead to a higher or overestimation. So, but what happened in reality that the molecules scattered the light away from the detector and less transmitted light reached the detector. So this is potentially causing an overestimation. So transport interferences, anything that could be in the reagents that might interfere with the absorption, you want to make sure that your standard contains the same reagents. So you can avoid this transfer interference potential. Volatilization, you did that in the lab. Some of you will do that on Wednesday. For calcium, we added a reagent called lanthanum chloride. Lanthanum chloride is added so that calcium and phosphorus don't form large molecules. So if you have calcium and phosphorus in your sample, they're going to form calcium phosphate. And not just calcium phosphate, they're going to form calcium pyrophosphate, which is a cluster of calcium phosphate molecules bound to each other. So that big cluster of calcium phosphate will precipitate down, no matter what the concentration of the acid is, they're going to precipitate. So when you aspirate your sample, calcium will not be aspirated into the flame, and you end up with underestimation. To avoid that, you add lanthanum chloride. Lanthanum would replace the calcium and react with phosphorus. Therefore, calcium will be released and will be solubilized and aspirated into the flame. So that's why for calcium determination, you will be adding lanthanum chloride, but for iron, that doesn't happen, there's no problem, so you don't add lanthanum chloride. Another issue is ionization, and we talked about that. If the flame is too hot, it's not only going to break the bonds, but it's going to convert atoms into ions. And in this case, you get underestimation because you won't get the same absorption of ions versus the atoms. The ions will absorb a different wavelength. So these are the potential interferences, potential sources of errors that might cause over or underestimation. Lastly here, 20 seconds and I'll let you go. So here's just differences between atomic absorption spectroscopy and inductively coupled plasma atomic emission spectroscopy. So both of them measure trace metal concentration. They have excellent precision and excellent accuracy. The advantage of AA, first of all, it's cheaper. It's been around for a long time. The problems are, already we know the problems. We already know the interferences. So it's very old technique, easy to work with. ICP, we can measure multiple elements without having to worry about clamps. Sometimes if you have this Ischl detector, you can do multiple elements in a single run. Stable at high temperature, you don't get ionization issue, you get atomization and excitation. And with ICP, you have much lower detection limits than AAS. If the lab is doing element analysis on a large set of sample, it's better off having ICP. It saves much more time. Okay, that's it. Thank you for staying 30 seconds more.